40 years ago, in 1985, Ken Perlin released a paper in which he described the Perlin noise algorithm for the first time. Its purpose is to create naturalistic randomness for use in computer graphics. He developed this algorithm in 1983 while working on CGI for the film Tron, because previous random generators were very machine-like and artificial, so it was hard to create realistic textures and animations. In contrast, Perlin noise produces smooth, continuous noise that fluctuates naturally. It outputs values in the range -1 to 1, and the randomness produced exists in a limited band of frequencies. This means the frequency and amplitude can be scaled to fit the use case. It is also free of patterns in the position or angle, so the noise space can be rotated and moved freely. The algorithm uses hypercubes to divide space into a regular grid. Hypercubes are lines in 1D space, squares in 2D, cubes in 3D, and so on. Every point in this grid has an associated random unit vector that defines the direction of a gradient from -1 to 1. When we sample the noise value at a point in space, the algorithm finds the corners of the surrounding hypercube, finds the displacement values between the sampled points in each corner, calculates the dot product between the displacement and gradient vectors for each corner, and finally it uses multilinear interpolation to combine the dot products for the sampled location. Multilinear interpolation takes the weighted average of values one dimension at a time, where the weighting is based on the distance between each value's location and the sampled point. For example, with bilinear interpolation in 2 dimensions, you interpolate between the top left and top right values, then the bottom left and bottom right values to produce top and bottom values. Then you interpolate between the top and bottom values to find your final value. Perlin noise smooths the position of the sampled point in the hypercube to get the interpolation position. This results in the final noise being smoother and more naturalistic. Perlin noise has revolutionized procedurally generated landscapes. It has been applied to producing naturalistic textures and natural motion, such as flames or trees waving in the wind. In 2001, Ken Perlin described simplex noise, a modification of Perlin noise to use simplexes rather than hypercubes. This takes its complexity from O of n times 2 to the n to O of n squared, where n is the number of dimensions. In 2002, he published a paper about improved Perlin noise, which optimizes his original noise algorithm through p-calculated gradients, and makes it continuous in the second derivative by a new smoothing function. This is my implementation of the improved Perlin noise algorithm for an arbitrary number of dimensions in Java. My algorithm uses an arbitrary number of dimensions to demonstrate how the complexity increases as the number of dimensions increase. We have a few pre-calculation functions to optimize the performance of the algorithm. This function calculates the corners of the hypercube in this current number of dimensions. It has a complexity of O times n to the 2 to the n, where n is the number of dimensions, because there are 2 to the n corners for a hypercube, and each corner has n dimensions, so there are n times 2 to the power of the n values to calculate. This function creates random gradient vectors for this number of dimensions. In one dimension, it creates a random value between -1 and 1. In every other dimension, it creates a random unit vector pointing in a random direction. This is so gradient vectors in one dimension have the same range of freedom as the gradient vectors in other dimensions. This is the main function of the algorithm. When we sample the value of noise at a point in space, we find the corners of the surrounding hypercube. We find the hashes for those corners. We find the random gradients for those hashes. We find the random gradients for those corners. We find the displacement from the sample point to the corner. And then we take the dot product of the displacement and the gradient vectors. Once we calculate the dot products for each of the corners, we interpolate between them and then return the value. Once we found the dot products, we interpolate between them to find the value at that point in space. To perform the multilinear interpolation, we loop over each axis of the space, performing linear interpolation between each pair of points on that axis. We then take the resulting point and use that for the next stage of linear interpolation until we only have one point left, which is the resulting value. To get the interpolation parameter for each axis, we find the part of the sampled position that is in the hypercube on that axis, and then we smooth it. We then interpolate for each pair of points on that axis and pass the resulting values onto the next iteration. We repeat this function until we have only one value left, which is the value at the sampled point. For smoothing the input position, we use the improved smoothing function from the 2002 paper. This implementation has a visualizer and a test suite. The test suite ensures that for the same seed, the same values are generated, the same point has the same gradient when sampled multiple times, and that generators are continuous in the first and second derivatives. The visualizer demonstrates one-dimensional generation, two-dimensional generation, and three-dimensional generation.